Hi everyone, we'll pick up on chapter 29 about magnetic fields where we left off with the last lecture. So this is part 2 of the chapter 29 lectures. You'll notice I've added a lot more typed words because I'm realizing that my handwritten notes on the PowerPoint slides aren't super legible for you. Okay, so we left off on this slide about the uniform magnetic field that we're going to be trying to use in a lot of our problems. Technically, a uniform magnetic field, just like a uniform electric field, is a bit hard to produce. One of the ways you can produce it is by looking at the field between two magnetic poles of permanent magnets that have relatively wide faces and a comparably small separation distance. So as long as we are looking here in this region near the center of the faces, sorry about that, this region near the center of the faces here, and not towards the edges where there's some fringing, we're going to call that a uniform magnetic field and work within that context. Okay, so what produces magnetic fields? One of the things that produces magnetic fields is electric currents. And actually in permanent magnets, I'm going to link you to a YouTube video that explains how the magnetic field is a quantum phenomenon in permanent magnets. But in the 1800s, a guy named Hans Christian Ørsted saw that compass needles deflected near a wire as soon as current began flowing through the wire. So therefore, he figured out current produces a magnetic field. One of the ways you can think of this is that a moving charge will produce a magnetic field. So current is moving charges. A moving charge will produce a magnetic field. Which way does that magnetic field point? Well, we're going to use a right-hand rule to talk about which way a magnetic field points. So if you take your thumb of your right hand, if you are right-handed like me, you got to put down your pen to do this. You take your thumb of your right hand, and just like this image shows, you point it in the direction that current is flowing. Then the direction that your fingers naturally curl around that wire is going to be the direction of the magnetic field. So you can see that with these blue lines here in this picture. That's the direction your right hand fingers would naturally curl if you point your thumb in the direction of current. Okay, so that was for a straight wire. What about for a loop of wire? So this is a loop of wire or a coil of wire or a circular current, right? You can also use the right-hand rule in this way. So see, your thumb is still pointed in the direction of current, and your fingers are curling in the direction of that magnetic field. Now notice these lines are actually loops. So our magnetic field lines are actually full loops, and you would call this loop of wire or this coil of wire a magnetic dipole. So just like a permanent magnet, this magnetic dipole has a north and south pole. Your magnetic field lines are emanating from the north pole and looping back around towards the south pole. Right, so that's another way to use the right-hand rule. Again, if you're right-handed like me and writing with your right hand, you've got to remember to put down your pen and use your right hand, because your left hand will give you the opposite answers here. Okay, so not only do currents create a magnetic field, but currents can feel a force from an external magnetic field. So this is where, just like with our electric field, it becomes important to think about whether we are talking about the field that is produced by the current or an external field that is doing something to the current. Whew, that's a little confusing, but it's just reading comprehension, right? Just like most of physics. So The force on an electric current in an external magnetic field can help us find a definition of B, or the magnetic field, right? So experiments show that the direction of force is always going to be perpendicular to the direction of current, and also perpendicular to the direction of the magnetic field. So if we look at our image to the right-hand side of this slide, looking at the top here, I have current going in this direction, kind of from front to back there. I have my magnetic field line shown there in blue, so we'll switch to blue, going from the north to the south pole of this horseshoe magnet. So the horseshoe magnet is just a bar magnet that's bent in a horseshoe shape and gives us an approximately uniform magnetic field there between the poles. Okay, so we have our field line going from north to south. This is yet another right-hand rule. So we take our right hand and we point our fingertips in the direction of current. So in that direction that I drew with the red line. We then twist our wrist around naturally. So our fingers will naturally bend in the direction of the magnetic field. And that lets us know the direction of the force by the way our thumb is naturally pointing. So in this top image, with the direction of the current and the magnetic field the way they are, the force that wire is going to feel from that external magnetic field is going to be a downward force. Now try it with the middle one. Point your fingers in the direction that the current points, so kind of from the back of the page to the front of the page. Twist your wrist around so that your fingers naturally bend in the direction of the magnetic field, and you'll see that your thumb is pointed up in this case, so that's letting you know the force is up. All of these right-hand rules are just ways to look at the cross product. So this is telling us that the force is the cross product of our current along that length of wire that's in the magnetic field. So we're going to define the length as our vector, crossed with the magnetic field. So here the order matters. Your fingers, when your hand is straight, are pointed in the direction of current. When your hand is bent, that's the second thing in the cross product. That's going to be the direction of your magnetic field. And that gives you your result, which is the direction of your thumb, the force. That's shown in this lower picture here with the right-hand rule. Now, if we just want to do the magnitude of the force, we should know from our experience with cross products with other things that we can just take the magnitude of the current, the length of the wire that's in that magnetic field, the magnitude of the magnetic field, and the sign of the angle between the current and the magnetic field. Now, if we're looking at only a little tiny section of current or a little bit of magnetic field, we can do a dF, dL, dV kind of relationship. That's going to be useful in two cases. Case one, the magnetic field is not uniform. So we're going to use that little bit if the magnetic field is not uniform and we need to do a summation of all of this. We can also use that in a second case, in a case where the wire is not straight, right? And so that angle between our magnetic field and our wire changes over the length of the wire. So two cases where that could be useful: magnetic field not uniform, or the wire is not straight. And that's just a more general expression for the force we're feeling, or the force our electric current is feeling in an external magnetic field. Units for our magnetic field and typical values that you're going to see. The SI unit, the System International Unit for a magnetic field, is the Tesla. So 1 Tesla is 1 Newton per amps times meters, right? A common non-SI unit that you sometimes see is the Gauss. A Tesla is a really, really strong magnetic field. So a Gauss is 10 to the minus 4 Teslas. It's just a magnitude of 10 smaller, right? Or 4 magnitudes of 10 smaller. But that's a non-SI unit, right? That's not in newtons and amps and meters in standard SI units, but it's easy enough to get from one to the other. Earth's field that you would measure with a compass is about, I actually have a typo there. This should say about half. No, that's actually right. Yeah, half times 10 to the minus 4 Teslas near the surface of the Earth. That's half a Gauss, right? That's why Gauss is a standard, or not SI, but a commonly used unit. Your refrigerator magnets are in the hundreds of Teslas. A strong electromagnet would be maybe about 2 Teslas. And superconducting magnets are getting up above 10 Teslas. So like things in the NMR machine that the chemistry department has are in that range. Much bigger than that, the magnetic field actually destroys the item that's being magnetized. So much bigger than that is not really possible without destroying the magnet. All right, we're going to pick up next time with some examples. I'm going to pause it here so you can take a break, get a drink, whatever you need to do, and we'll pick up with some examples next time.